Alright, hey guys, I'm going to go over the derivation that we did today in class one more time, so you have it on. I have a record up here. You can go back and look at it for reference. Alright, so today in class we talked about how if we have a velocity v versus time t graph for an object moving at constant acceleration, should be in a straight line, right? Now you already derived in class, you guys together, y'all derived the equation v equals at plus v naught, right? Y'all did that in class already, so we might use that later. And then we also had already derived, previously last week, we derived x equals vt plus x naught. So we're going to need both of those here in a little bit. But when we have a velocity time graph, turns out that if we take this equation here and we manipulate it a little bit, and we take, I'm going to rewrite it down here a little bit. We say x equals vt plus x naught, and I'm going to subtract x naught from both sides, minus x naught from both sides, and I get x minus x naught equals vt. We get this guy right here, right? Now that equation tells us that the change in position, our final position minus our initial position, which is displacement, that equals velocity times time. That equals velocity times time. Now, that's really useful because we already have a velocity time graph. So we just take whatever our value is here, velocity value, write that value there, and we multiply that by this value down here times time. We get v times t, and that should give us our displacement. The problem is, this is a triangle, right? It's a triangle, and we don't really know exactly. The velocity is changing. In other words, it's starting at 0 in this graph, going up a little bit, up to here. So what velocity do we use? So today in class we talked about how if we find the area under the curve, or in this case it's a straight line, but we always just say area under the curve. If we find the area under here, right? The area under the graph is the velocity times the time. In this case, it's a triangle, so it's going to be 1/2 the velocity times time, right? But it's the same. It's still velocity times time, right? It's still v times t. It's just 1/2 of that. But we still v times t, right? It's still v times t. So it should still give us or displacement rather. It should still give us displacement. So today in class we talked about how if we have a graph that looks like this. Again, velocity times time. And instead of starting at the origin, it starts up here somewhere. It starts right here and goes like that in a straight line. This spot here is vi or v naught. Sometimes I use both. And it goes up to here, and that's vf. That's final velocity, right? So we said, all right, well, hard to see that. Let me just move down. There we go. The vi here and the vf. So we said, okay, all right, well, what if we cut this graph into pieces? And I say, all right, well, I know how to find the area of a rectangle. That's easy. That's base times the height. That's going to be the area of this area here, right? And I can find the area of a triangle. That's 1/2 base times the height. And we add those two up, and we get total area. And because one axis is velocity, the other is height, those are the only variables we have here, right? Base height, base and height. Base times height are, in this case, velocity and time, right? So if we multiply them together, we should get displacement, which is what we said here, right? So that's all we're doing. We're just doing velocity times time to get displacement, except that in this case, it just happens to be one of them is in a triangle, so we had to do 1/2 base times height plus the other rectangle. Okay, so well, let's do the derivation and we'll see how it works out. All right, so here's our graph again. V t. So here's v naught, vf. All right, so we know that the area, or x minus x naught equals area. Oh, going off the page here. Sorry, area under curve or graph, however you want to say it, right? That's x naught. Okay, so area under the curve, we already said that's the 1/2 the triangle part of it, right? This part here, all that, plus the rectangle part, which is base times height. That's that part, right? We add those two parts together, we get total area, and it's just base times height plus base times height. Velocity times time plus velocity times time. That gives us displacement. So that equals x minus x naught. Now the rest is just algebra and substitution. So we're just going to plug in for base. The base of our rectangle is time. So whenever I see a b, I'm going to plug in a t. The h is a little different. We'll talk about that in a second. So let's write it out. So we're going to have, I'll go down here. We'll go x minus x naught. That equals 1/2 base times height. 1/2. The base is time. It's on the x-axis, so it's t. And then it's the height of the triangle. Now remember, the triangle starts here and goes up to here. It's not this whole height, right? It's not just VF, right? It's VF. It's this much minus this much. This much minus this. Or you might say the change in velocity. So we have our total velocity all the way up to the top, but then we got to subtract this one. We got to get rid of this area down here because we don't want to count it, right? It only goes from here to here. So we just say VF minus V naught. VF minus V naught. That's the height of our triangle, right? It's just this from here to here. Plus base times height. That's, again, time to the height of our rectangle. Now the height of a rectangle only goes from this here up to here. We don't need the whole all up to here. We don't need all that, right? It's just from here to V naught. So our height of our rectangle is V naught. Now we're going to substitute in something here. This here is the same as our other equation from before. If we rearranged this, say minus V naught here, minus V naught there, these cancel, and we get V minus V naught equals, it's hard to see that, huh? Let me put another paper there. There we go. V minus V naught equals AT. Now look, VF minus V naught. V minus is the same thing, right? So this, the same as this. So if they equal if this equals AT, then I can substitute AT in down here since they equal each other, right? They're the same thing, so I'll just plug one in for the other. So I'll put an AT in down here. So I get x minus x naught equals 1/2 t times AT plus V naught t. No, I just put those around. Same difference. From here, it's pretty much just basic algebra. We're gonna take this t and times these two terms together. So t times t is t squared, and then I'm gonna move the x naught over from this side to this side just because it makes it a little neater. So these cancel, right? And then I get x equals 1/2 AT squared now plus V naught t, initial velocity, plus x naught, starting position. And there it is. There's our final equation. And isn't she a beaut? All right. Hope that helped. If you have any other questions, email me, message me on Remind. See you guys tomorrow. Have a great day.